Why are you here? Because you need to do this course for grades. Why am I here? I need to teach you and grade it. Okay. So another thing is what we can do is we can learn together a very interesting part, that is 4-terminal technique, carrier concentration and band gap. Okay. These are very interesting properties of semiconductors. 4-terminal technique lets you know about the conductivity of a semiconductor, right? That's what we are going to find out today. So it is written semiconductor resistivity measurement. It's basically that resistivity is inversely proportional to conductivity, right? Higher the conductivity, lower the resistivity. Okay. Next is to obtain carrier concentration of semiconductors. It's basically we need to know how much carriers are inside that can conduct electricity, right? We don't want bad semiconductor. We want to apply very low voltage and get very high conduction, right? Okay. Then to determine the band gap of a semiconductor, which is very interesting property, which is I am going to explain in the last 3 slides. Okay. What are semiconductors? As I told you, materials with resistivity. Okay. When I say materials with resistivity lying between metals and insulators, is basically saying that the conductivity also lies between metals and insulators. Metals are conductors, right? Okay. So you can see the resistivity range 10 to minus 3 20 by 8. So you can see here the green ones are all the conductors that can conduct electricity. 10 to minus 8, 1.7. So basically it is on the left hand side, right? So it's basically a conductor. Its resistivity is very less. That means its conductivity is very high. Okay? So the conductivity lies in the range of 10 to minus 8 to 10 by 3, right? 1 by. Okay. Silicon, germanium, gallium arsenide, you must have heard of these names. These are all semiconductors, right? What you see in the diagrammatic representation is called a lattice. It's basically the arrangement of silicon atoms, gallium arsenide, or germanium atoms, right? You must have heard of covalent bonding and all. This is all on that. Okay, it's very nice structuring in a wafer, in a crystal, right? And these are semiconductors because, okay, they are semiconductors because of their intrinsic properties. It's not like you have done anything. They are own semiconductors, okay? Okay. So silicon is a semiconductor, you can see the range, it is lying in this range. And glass is basically glass, wood, plastic, rubber, all are insulators, right? Electrical conductivity, you can see materials property that quantifies the ease with which charges flow, right? Under the influence of electric field. Okay. Resistivity is inversely proportional to conductivity, rho is equal to 1 by sigma. Resistance. What is the difference between resistance and resistivity? Okay, let us say I say that a material has a resistivity of something. That means that that material is having an intrinsic property that says that its resistivity is this. It can move the charge carriers up to amount of this much. But resistance is dependent on the dimensions of that material, of that wafer, right? The material I am talking about. So you can see R is equal to V by I is equal to rho into length by area. So it's basically saying that R is equal to resistivity times length by area. Now you have iPhone cables, right? Let us say if it is very long cable. So L is very high and it is very thin, very thin cable. What happens to resistance? So L is large, WD is small, right? Because it is very thin. So it's the cross section area. It is very thin. So WD is small, L is large, resistance becomes high, right? So resistance is very high. That's why you have iPhone cables very small. It's not very big, right? If you have something like 5 or 6 meters, it will like take ages to charge your phone, right? Let us say your iPhone cable is very small. Smaller than it is now, and WD is very high, that is the cross section area is very thick, resistance is very low, right? So all the conduction is very easy through the wire and you can charge your phone very fast, right? That's what it says. Okay, so resistance is basically dependent on the system that you are taking, right? But resistivity is dependent on the intrinsic property of that material that it is made of. Okay, sheet resistance. It's for a two-dimensional thin film system. It's basically a three-dimensional system. This is two-dimensional because its W is very small. So let us say I give you a thin film, a wafer or something, right? I give you a wafer. That wafer you are going to talk about sheet resistance, right? Sheet resistance basically kind of resistance. The only difference is that since it is very thin, the effects of current going into different dimensions is very small, right? Because it's only a two-dimensional film system. So that's why we always talk about sheet resistance. So one thing you have to be clear about, that whenever you have a very thin wafer or very thin substrate, you have to find out the resistance of. You must find out sheet resistance, right? Not resistance. Okay, sheet resistance, you can see that it is equals to rho by W, which is equals to R into correction factor. What is R? It's V by I. So let us say I give you a wafer, you apply some current, you find out some voltage, right? What happens is you multiply it by correction factor. So you get a sheet resistance. So in this lab today, you are going to find out the sheet resistance of the germanium wafer, which is N-type. Okay? 4-point probe. Okay. You can see here 4 probes, right? So in the outermost probes you have to apply current, and the innermost probes, the second and third probe, you have to find out what is the voltage between them, right? That's how you calculate V by I, and you just multiply by the correction factor. Now what is the correction factor? Correction factor is some numerical value that is taking care of the dimensions of the system, right? The dimensions of the system, the shape of the system, and the probe spacing that you have in a 4-point probe resistance measurement. Now you must be thinking, what is a 4-point probe? Okay. You can pass it on to your friends each side. You can see there are 4 probes. You just have to put a wafer beneath it and then press it. And the 3 wires are basically, one is for I, one is for V, and the third one is for temperature. Right? I will tell you why we are going to do that later. Okay? Okay. Now let us say you have a square wafer. Okay? You have a square wafer. So what happens to A and D? What is the relation between A and D? A is equals to D, right? A by D is equals to 1. So this is the curve, A by D is equals to 1, you have to follow. Right? Now, what is D by S? So S you can see in the probe spacing, that is the probe spacing. So it's basically 2 mm, that is 0.2 centimeters. Right? Let us say D is equals to 1 centimeter. I give you a wafer of 1 centimeter cross 1 centimeter. Okay? So D is equals to 1 centimeter. S is equals to 0.2 centimeter, that is already provided to you. What is D by S? Yeah, D by S, what is it? 1 divided by 0.2 is equals to 5, right? So D by S becomes 5. You follow this D by S value. Follow this value. You come to this point because A by D is equals to 1 for your square wafer. You get the value of 3.5. Yeah, there's a point. I could not see this. So yes, there's 3.5. Okay. So what you do is you do V by I multiplied by this correction factor. That's how you find out the sheet resistance. So you'll be finding out the sheet resistance for the given wafer at 25 degrees centigrade. That is the room temperature. Okay? Okay, so you can see also here that rho is equals to Rs into W. So as soon as you find out Rs, you multiply it by the thickness of the wafer and you get resistivity. Right? Types of semiconductor. Okay, the semiconductor are of 2 types, intrinsic and extrinsic. The intrinsic one is something like natural. It is provided to you by divine superpower, right? So there's nothing touched by mankind and it's intrinsic. So what happens is, it is said to be intrinsic because it does not have any external factors into it, influencing into it, right? So the number of excited electrons and holes are equal, n is equal to p. Now when I say holes, what are holes? What are holes? What are holes? Holes. Okay, holes are holes. Okay. Wow. The best definition I've ever heard. Okay, so the number of electrons is equal to number of holes. That means that, let us say, there is an electron sitting inside the system. When you excite it, when you give it energy, it moves to some other place, right? It starts conducting. As soon as this goes to some place, it is basically leaving behind a hole, right? It is basically leaving behind a hole. Okay. So the number of excited electrons and holes are equal, n is equals to p. So everything is settled down in intrinsic one. But what is extrinsic? Why do we need extrinsic? Extrinsic is basically semiconductor with impurities, that is dopant inside it. So you can say the concentration of one type of charge carrier is greater than another. So n is greater than p. N is denoted for electrons are denoted by n, holes are denoted by p. So n is very greater than p for an n-type semiconductor. So basically what happens is, in an n-type semiconductor you have majority as electrons, right? You have majority as electrons, n-type semiconductor. P-type has holes. Okay. What is Avogadro's number? 6.023, right? Okay. This is 1 mole of material, right? Of any impurity. Let us say I ask you that since you are fabricating something, you are making some germanium wafer or something, I just put some impurities inside. So I say I just put inside a pinch of impurities. And a pinch of impurities may be something like, let us say, 1 milligrams, so 10 by minus 3 grams, right? Or something like, I say I put 0.01 moles of impurity, right? So 0.01 moles of impurity means how many atoms? 6.023 into 10 power 21, right? 0.01 mole. Now you can imagine, I am just putting 0.01 moles. It's like 1 milligrams. It's like you can see a pinch of salt. I'm just putting that inside the system, and it will give, let us say, one atom is giving 1 electron. It's contributing somehow. What happens is, you are giving inside the system 10 power 21 electrons. That is a huge number, right? So generally your intrinsic has n is equals to p is equals to 10 power 5, 10 power 6. But as soon as I add just a pinch of impurities, it is going to increase the charge carrier concentration by 10 power 15 or 10 power 16, right? So we go to 10 power 25. So it is huge. Why do you need extrinsic semiconductor? Because you want good conductivity out of the system. You don't want something like I apply 2 or 3 or 5 volts and it is still moving very slowly. So you don't want that, right? You want your iPhones to give the best capacitive current or something, right? So the screen should light up like very bright. It should not be like okay, you click once, you open one browser and it is taking 1 hour or something to open it, right? Doping in semiconductors. Why? As I told you, because we need to change its electrical properties, basically change the charge carrier concentration, right? N-type dopant, you can say that it is called dopant or donor because it is giving extra electrons into the system. When I say it is an acceptor, P-type dopant is an acceptor, it means that it is accepting electrons or it is donating holes, right? Accepting electrons and donating holes are a similar function, right? Holes are the counterpart of electrons and all. Okay? Any doubts? Any status of the doubts? Okay. Doped silicon lattice. You can see silicon was very happy here, natural way. But then something happened to it. I added a pinch of impurities. And what happens is there is a P, that is phosphorus atom sitting. Now if you remember the periodic table, silicon was in the group 4, right, in carbon table, and phosphorus on the right hand side of the table, right? It is having 1 extra electron in the valence shell, right? So it is having 5 electrons in the valence shell. Now when it comes and substitutes that silicon inside, because I have given it, I have induced the impurities inside, now phosphorus is going to replace silicon. What it is happening is, 1 atom is bringing 1 electron with it, right? That electron is free. Now you can apply electric field and conduct through it, right? You see aluminum is on the left hand side. It has 1 less electron, so it has 3 electrons. So just to think of, you can say that it has 4 electrons in 1 hole. Can you say? Just to make it clear to you, it's basically kind of 4 electrons in 1 hole. So it is basically bringing one hole with it. So it is basically becoming p-type. So there is silicon n-type, there is silicon p-type, like doped germanium lattice also. Germanium has 4 and 4, you can see it is sharing with 4 atoms. Then arsenic is bringing 1 electron and indium is bringing 1 hole. Right? That's how you convert it to n-type and p-type semiconductors. Okay, why do you need a p-type and n-type semiconductor? Why do you need a p and n-type semiconductor? Okay, that's the interesting part. Okay, you see this switch? This is a mechanical switch, right? This is a mechanical switch. It does not have anything to do with providing current or something. It just have to do that. You just mechanically do it, and then it touches the wires, and then it switches on the light. Right? It is mechanical. What is an electrical switch? Electrical switch is something that you apply some potential across it, and then you control whether the current should pass through it or not. Now, P and N junctions are very important. What is a P and N junction? You take one semiconductor of P type, you take another semiconductor of N type, you join them. What happens to it is very interesting because I have just taught it to the third year, so I think you will be learning it soon. But just to give you an idea, a PN junction is like an electrical switch. What you do is when you apply positive current, it will conduct electricity. But if you apply negative potential or negative current, it will not. Right? So that's how it's an electrical switch. That's why you need a P and N type semiconductor. Now you have in your laptops and iPhones there is something called a transistor. That transistor has PNP junction transistor, right? That PNP is basically P-type, N-type semiconductors bonded with each other. Right? Okay. Carrier concentration versus resistivity curve. You can see the resistivity and carrier concentration. As I said, let us say I add a pinch of impurities. Let us say I add something at 10 by 18. Can you see how much is the difference? That is log versus log curve. So it is 10, this is 11, 12, no sorry, this is 10, this is 20, this is 30, this is 40, this is 50. So earlier it was 50, that is very high resistivity. And now it is something like 0.01, right? So it decreased hugely. Just adding a range of impurities. Okay, this is the standard curve. You can see P and N type have different kind of curves, so you just have to follow these curves. This is germanium. So you may be seeing this graph. You may be using this graph in your experiment. Okay. Mobility. Okay.
Oh my god.
Yes. Okay. Mobility is something the intrinsic property as well of a material. Okay. Let us say you have some group of your fellow students going on a trip or something, right? But they are not your good friends, they are just your colleagues. So you will be, if they ask you to go, it's your personal opinion that you want to go or not. That is basically mobility. It's basically that you want to go or not, that is dependent on you, right? How much mobile are you just to think of that you can go with a group of strangers or something like fellow students who you are not good friends with. But let us say your other group of friends is also going with you, right? 5 or 6 friends say, okay, let's go together. Then that decision is being influenced by a group of friends, that is by the number of people. That means that is conductivity, right? Because conductivity is dependent on, you can see here, the conductivity is dependent on n q mu. So it's basically saying that if there is large n, then it is influencing your conductivity, right? So basically the conductivity is being influenced by large carrier concentration. So n q mu, what is q? Is the charge, 1.6 on this side. Okay? Okay, these are all the formulas. I think you can go it's all like just very easy formulas. You might be knowing it. It is the drift velocity per unit applied field. Is basically the velocity divided by applied field. That is what is mobility. Okay. As I said, rho is equals to 1 by sigma. So you just do 1 by sigma, it is equals to 1 by n cube u, right? Now this is a graph that shows the mobility versus impurity concentration. You can also see this impurity concentration 10 by 18 is decreasing the mobility. Now I said mobility is an intrinsic property. I said mobility is an intrinsic property, but it is not exactly an intrinsic property. You can change it by impurities, right? You can change the intrinsic system as well using the impurities. Okay, you can see silicon, germanium, gallium arsenide, they have different curves. You may be following this curve, germanium, right here. Temperature effect on mobility. Okay, I'm going to give another silly example, so please don't laugh. This is a small room, right? Let us say there are 100 people inside it, right? And what I do, you are standing here and you have to go out of that door, right? Now 100 people are inside and suddenly I increase the temperature. I have a level inside. So I increase the temperature to 40 degrees like a furnace. And what happens is you want to run out from there to there. But the point is everybody is wanting to run out, right? So what happens? Can you run out?
Cannot.
Everybody is like ending up pushing each other, right? So that what happens is in the lattice interaction, when you increase the temperature, the mobility decreases because everywhere they are just striking each other and they cannot move, right? Everybody wants to come out. So lattice interaction is something like this mobility. Impurity interaction is something dependent on impurities. Now impurities, as I said, it is a free electron. It can do anything. It's like a big boss. So it's like a Superman who can fly through this room, right? So he can go across. So as temperature increases, he will just run out. So okay, so mu increases. That's why I said it's a silly example. Okay. Okay, so impurity interaction and lattice interaction are two mobilities that define some mobility. Okay?
Oh, come on.
Energy bands of semiconductors. Okay. So I said the band gap, right? What is the band gap? The band gap is something that is valence band and conduction band difference. What is the valence band? Yeah, okay. Valence band means that, you know, valence electrons, they are sitting with some energy, right? So that energy band is called a valence band. Okay? That energy band is called a valence band because valence electrons are sitting on that band. But what is a conduction band? A conduction band is a band of energies in which if electron moves to, let us say it is excited to that state, it will start conducting, right? And once it starts conducting, it's a good news for you guys. Okay? Okay, so Eg is the band gap. You can say that, let us say there is an electron sitting over here that is in the outermost shell. You apply some potential. You have to apply some potential that is greater than this gap, right? Because you want to give it energy at least to this much so that it can go to conduction band and start conducting, right? As soon as it goes to conduction band, it starts conducting. Now this Eg is something that is intrinsic property as well. So that is like God made. So you have to find out Eg. So today's experiment is going to be about finding Eg as well, the band gap of a material. The material is germanium wafer. Okay? Okay. This is the curve that is important part of your experiment today. So I will ask you to pay attention a little more. As you can see, this is 1 by T, right? This is 1 by temperature. What happens if I increase the temperature? Which part of the curve I am talking about? Left hand side, right? So that slope, that big slope, it's called an intrinsic region. So basically, what we are having is at higher temperature, we are into intrinsic slope. And in the low temperature region, we have ionization slope, right? In the middle part, it's extrinsic. So what happens is, we are going to find out that intrinsic slope, which is Eg by 2k, from the measurement we are going to do today. So that will give you Eg because k is Boltzmann constant. You might be knowing it, right? K is Boltzmann constant. Like kT, right? Okay. So low temperature, you can see T is less than Ts, ionization range, ionization of dopants. What is ionization of dopants? Ionization, what is ionization? It's making ions, right? Out of dopants. So it's basically taking electrons or giving electrons to it. That is called ionization. When you have a neutral particle, it's a neutral particle, but when you take its charge or you give it the charge, it is basically you are ionizing the dopant, right? So ionization of dopants is in the low temperature range, that is in the right hand side of the curve. You don't have to do anything with that. The medium temperature range is extrinsic, all dopants ionized, and high temperature you have only intrinsic atoms ionized. Why? Why you have at high temperature only intrinsic atoms ionized? I tell you, because you need some high temperature to excite these electrons to here, right? You need high temperature because you need to cross that band gap, that Eg. So let us say this Eg is 1.1 electron volt or 1 electron volt. So basically you have to apply 1 volt of potential, right? Or you have to heat to 1 electron volt of energy. What is 1 electron volt of energy? We can convert it to joule, right? So basically 1 electron volt of heat energy you have to provide to excite the electrons. So that's why when we go to high temperature, we ionize these, and then you can find out what is Eg, because at certain temperature it will suddenly shoot up. It will say that, okay, this is the temperature I needed, right, to cross that band gap. So this is the curve, as you can see, ln n. What is n? Charge carrier concentration. So charge carrier concentration is ln n, so is 1 by t. Now in intrinsic range, n is proportional to this part, that is the curve I was talking about. That was log curve, this is only n. Okay, so when you take ln on both sides, you can see that 1 by t, with respect to 1 by t, it has a slope of Ag by 2k, right? So resistivity is equals to 1 by nq mu, and is equals to a into exponential of this. Ln rho is equals to this. So you just plot a curve of ln rho versus 1 by t. In your experiment, you have to plot a curve of ln rho versus 1 by t and find out the slope through linear fit, right? Okay. Let us say you get a curve like this, right? And you are doing Excel. So there are many good softwares. If you can use them, then it's okay. But if you want to use Excel, I would like to tell you how to linear fit the regime. So now you can see there's like 4 or 5 points, 4 points of linear fit, right? Only those points you have to fit. You have to ignore the other part. So first step is to identify what is the linear region. Right? Let us say you have some values like these. Right? You have some values like these. First you identify what is the linear region you have to fit. So you take a straight line and then you see, okay, this one is the one. So you show this line in your report, right, that this is the region we are considering for linear fit, and then you find the slope between this and this. How do you find the slope? y2 minus y1 divided by x2 minus x1, right? Okay, this one. So you just see this minus this divided by this minus this. Okay, so you get a slope of 3, and then you choose the units carefully, everything, and then find out Eg. Okay, any doubts about it? Any doubts? No. Okay, calculation, measure the current and voltage at 25 degrees centigrade is the first part you are going to do, room temperature. Then check the units carefully because we have tried to confuse you as much as possible. Okay, select the correct range of 1 by t to plot the slope and find the intrinsic region. There is one fun fact that germanium is actually an insulator at low temperature and a good conductor at high temperature. Okay, express Eg in terms of electron volts. You know how to convert it to. Which report do they have?
Which format?
Formal? Informal. Oh, lucky guys. Okay, so informal, just do something. Okay, I mean, yeah. So, as you can see in your sheet, there is a sheet provided to you. What is written in it? What is the first column over it? Temperature, right? So it is the temperature in degree centigrade, and then you have to convert it to Kelvin. How? Okay. Then voltage. So first of all, you will be providing the current that we are going to apply to it. So Kyanbun is going to explain you about these things. So be careful about the system because it is very sensitive. So don't touch all those devices. You can see the 4 probe here, but don't touch those. Okay? And it's very sensitive. As soon as something happens, just call me or Kyanbun. Okay? And if you have any doubt, just come to me. It's alright. Okay? Okay.
So am I
Yeah, I think you guys can start.